Okay, so we're here where we want to show that the Upwind scheme can actually be interpreted as a linear interpolation. Okay, so here is the scheme. I've explained this point already in the previous video, and so here basically I just repeated this the same figure over here. Now the slope once again of the characteristic is 1 over c, okay, which means if I take delta t all over the distance from A to Q, it should be equal to the slope of this, which is 1 over c, and this can be written as this. Well, using the CFL number, I can write c delta t as a nu or nu delta x. So absolute value of AQ is equal to this, right? The distance from A to Q is also equal to this. Also, I need to get the distance from Q to B. Okay, the distance from Q to B is equal to the distance from A to B minus the distance from A to Q. Okay, so that is A to B is delta x, and A to Q we just found is nu delta x. All right, now we are finding the distance from A to Q and the distance from B to Q because we want to use those to interpolate the value of u at Q, right? If you go back to here, that is what this is saying. That's what you need. Okay. Okay. So so we have them from this figure. So using the value of u at A and the value of u at B, we want to interpolate for the value of u at Q. So u at Q will be equal to the value the distance from Q to B, all right, divided by the total distance, which is delta x, multiplied by the value of u at A, which is ujn, plus I can take the distance from A to Q, right, divided by the total distance multiplied by the value of u at B, and that is equal to uj minus 1n. So basically this here is using the interpolation thing that we talked about earlier. Okay, and so now if you go back here, the QB over delta x divided through by delta x, you get 1 minus v. So this is basically 1 minus v. AQ over delta x is just v, right? If I divide through by delta x, I get v. So this guy here is v. So I have 1 minus v and ujn plus v uj minus 1n. So uq, so the value of u at q is given by this. Okay, but again the value of u at q is the same as the value of u at p because the value of u is fixed, is constant along the characteristic, which means that the value of u at q can be replaced by the value of u at p here, which is ujn plus 1, and that should be equal to the right hand side, which is this. And so you can actually interpret the Upwind scheme as an interpolation, a linear interpolation from the Q to P here. All right. Okay. So that is the Upwind scheme. We want to look at a simple example of how this works. Okay. So we'll just look at a very simple example. I'll send you the code for this. So you consider a 1D hyperbolic problem. So it's the adverting equation. X lies between 0 and 1, t is greater than 0. This is the initial condition. When t is 0, you have this something like a step function, right? So it's equal to this, or a hat, for x lying between 0.2 and 0.4, it is 0 elsewhere. Okay? So I'll send you a computer code which I use to do this. So you can use to solve the hyperbolic using the hyperbolic equation using delta x to be 0.01, delta t I chose it to be 0.001, I chose c to be 0.5, it's positive, and then you just apply the Upwind scheme that we've talked about. Okay, so when t is 0, when you just plot this initial condition, I'll show you the figures. And then at t is 0.5, I mean 0.1, 0.5, and 1 are shown here. So the solution when you solve it using the Upwind scheme. So when t is 0, this is the initial condition. Everywhere it's 0, but between 2 and 0.4, you have this function here, which is basically decreasing, and is 0. Okay, as time increases, this hump here, see that this hump does not retain the same shape. Okay, it reduces, it becomes smoother here, but it is moved to the right, and then at t is 0.5 it's moved even further, at t is equal to 1 it moved even further. But as it's moving, notice that the height is also decreasing. Okay, we'll talk about that. So it's basically dispersing at its go. There's damping and dispersion going on as it's moving. I made a like a video. Let's see if that works. I'll try it. See if it works. Then you can just. If not, I'll probably. Okay. So play. Let's play and see. Okay. So you have the hump initially, which is basically propagating to the right because c is positive, but as it's going, notice that the hump there is decreasing as it's moving along. Okay, so this is just a simple example. You can look at different shapes, different initial shapes, and how they move. So its initial hump immediately decreases and then begins to move to the right. Okay, so that is a simple example of using the upwind scheme. So we'll discuss why there is damping and there's dispersion. Right, dispersion is this thing is getting wider, it doesn't retain the shape that it starts with, and then it's also decreasing as well as it's going. Why is that the case? So we'll look at that. Okay, so basically you can use Fourier analysis to basically analyze why there is damping and why there's dispersion in this case. All right, I would like to do that in my next video because that'll probably take more time than I will have my listing. Okay, so I'll discuss that next.